Welcome to RISE Learning Machines seminars. I'm Olof Mogren. I'm a machine learning researcher here at RISE. RISE is Sweden's public research institute, and this is our open weekly seminar on AI and machine learning. The meeting will be recorded. Let us know if you want to be removed from this recording prior to being published on YouTube. On YouTube, you can also find a wonderful list of amazing talks that we've recorded over the years. Now I will hand over the word to my colleague Delia, who will introduce the speaker today.
Thanks. Yeah, I'm so happy to have Udi here today talking with us. He's a senior researcher engineer at Adobe Research, where he focuses on human-centered AI for audio creativity. He holds a PhD in music technology from the Music and Audio Research Laboratory in NYU. He also has a master's in music science and technology from Stanford and another master's in information technologies from Pompeu Fabra. He is highly involved in the MIR community, and this last year he was one of the 3 general chairs from the famous Izmir conference, where it was held in San Francisco, and I heard it was a success. I'm really bummed that I missed it. Oriol has helped develop quite a lot of open source MIR packages, some of them which really saved my PhD, like Librosa, Mir Eval, and he has also contributed to PyTorch. He also plays guitar, violin, cajon, sings, screams, and we all know he does this really well because if you go to his mirror, we can see him doing all of this in the jam sessions that he usually animates. In this talk, he's going to talk about his latest publications on generative AI for sound design, and I'm really looking forward to it. I hand it over to you, Oriol. Thank you.
Thank you, Delia and Olof. Thanks for the great introduction. I feel honored to be here. Okay, so I'm gonna try to share my screen, and yeah, we missed you, Delia, at Izmir this year. Let me see if I can do this. Oh, I need to share audio, share sound. Okay, and okay. Can you hear my screen? Can you see? Oh my goodness. Can you see the screen? Can you hear the sound?
Yes.
All right. Yeah. So hello, everybody. I'm really excited to be talking about some of the latest work and publications that we've done at Adobe Research, mostly focused on generative AI for sound design. So to begin with, what is sound design? We can define sound design as the art and practice of creating audio elementals for various media, including films, television, video games, theater, etc. And a big component of sound design is coming up coming up with the ideas to map specific sounds to create the creations that you want, that you might be working with. And I'm going to just let an expert Foley artist speak about it. Oh, is this? There you go.
These are actually just toilet plungers.
Meet Joanna Fang, Foley artist for PlayStation Studios and a master at sonically translating our world through works like God of War Ragnarok.
So as we can see, it can be extremely difficult to have access to so many props and recording gear to come up with these high quality sounds. And not only that, but there's a big component of sound design that entails having to carefully tune so many knobs and presets to synchronize the final sounds to a given video, or to just create like the perfect sound for your creation. And this can be a daunting and tedious task, and we believe that we could help creators by having an AI assistant to help with this. And that's where the Sound Design AI Group, or SODA, comes in. And that's exactly what we are aiming to do. That is a relatively new research team at Adobe Research. We're all based in San Francisco, California. And this is a little sound generated by one of our models. And this is just the three of us. It's just three researchers. That's Justin Salomon, Brem Sitharaman, and myself. And we have a lot of interns during the summer that help us advance all of this technology. And in the meantime, we try to put a bunch of this research into Adobe's product. I'm gonna play a little video of Justin talking at one of these big Adobe conferences about some of the latest research that we did. It's like a 1.5 minute long video. Let's just do it.
We all know that sound design is critical to storytelling and video. Please welcome to the stage Justin Salomon with Project Supersonic.
Yeah. All right. Wouldn't it be great if I could just generate sounds for my project right in the timeline? I'm going to go here and type in forest ambience. There we go. Let's have a listen.
Sounds like a forest to me.
All right. I can hit subject selection. Now I can hover over it, and when I click on the spaceship, it's going to write a prompt for me. There we go. Check it out. We get a spaceship taking off from a forest planet. Are we ready for our spaceship? All right, here we go. Sweet. We've got liftoff. So check this out. I am going to hit record, and I'm going to imitate the monster growls with my voice. Rah! 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 All right, so... we got the growls down. Now let's see what we get back. I'm going to type in monster growl, and I'm going to hit generate. Oh, there we go. Let's crank up the volume. I want to see what we got. All right, are we ready, everyone?
Yes.
Let's see what we get.
Whoa.
All right, so this is some of the technology that we did, and now this is the last piece of technology that I wanted to show that just came up from our group. This is generative extend, and you can already try it out if you have Premiere Pro. And I'll just have a YouTuber talk about what it does.
You're in the middle of editing when you find a clip that you wish were just a little longer. With Adobe's new Generative Extend, you can now generate extra frames to perfectly fill the gap. For example, I have a clip here that I want to make a bit longer. Watch how I can extend it by dragging the end over here. Let's give it a few seconds to process, and just like that, new frames have been added, and you won't even notice where the AI steps in. Generative Extend also works on audio. I had an audio clip of people clapping that felt a little too short, so I extended it, and just like that, Premiere generated more applause that matches the original audio. This feature is currently available in public beta, which means you can already use it yourself, so make sure you give it a try.
All right, so yeah, it's really cool to be able to train all of these models and have them being used by so many people using Adobe products. But this is more of an academic talk, so enough of all the corporate stuff, and let's just go deep into the publications. Okay, so the outline of the talk is going to be, I'm going to give a little bit of an overview, very high level, on diffusion models for audio generation. And that's going to be the foundation of the three different works that I want to focus on. The first one is going to be SILA. I'm going to talk about what that actually is. A sketch to sound and MultiFoley. All of these are papers that we just recently published. Okay, so I'm going to start with the diffusion models for audio generation. And again, this is a very high level overview and hopefully not super technical. So ideally, you have this model that is a diffusion model that you have trained to generate audio unconditionally. And what this model would do is to basically generate this high quality, ideally, set of audio samples that you can listen to. Usually, what you do when you train these models is to train them conditionally, conditioned on some sort of signal. In our case, we use text, the text prompt. So you condition your diffusion model, your diffusion process to generate an audio based on text. But this condition could be other sort of modality. It's very common in the literature to use text. So the way these diffusion models work is actually they not only take the text as input, but they take noise. They take Gaussian noise of the same dimensionality of your output. So if you want to generate 10 seconds of audio, you're going to have to input 10 seconds of Gaussian noise. And what this magical little drawing, this diffusion model does, is to iteratively denoise this pure Gaussian noise so that after several iterations, you get this high quality audio signal. Now, this high quality audio is very high dimensional. For high quality audio, we're talking here about 48,000 hertz. That's the sampling rate, which means that there's 48,000 data points for 1 second of audio. And that's actually more if you have stereo or like 5.1 or other like more ambisonic audios. So that's very high dimensional. And these models, you could help them out by a lot if you could compress all of this information in a much more compact space. So typically you don't operate in this time domain, but you operate in this latent space. And that's why we not use like just diffusion models, but we use latent diffusion models. So what these do is actually operate in this latent space that then you will need a decoder that is already pre-trained that will convert whatever you have in this latent space into the time domain. So hopefully this latent space contains all the relevant information such that you can produce high quality audio from there. The only difference then is that you don't feed Gaussian noise in the time domain, but you feed Gaussian noise in the latent space domain, which is again much more compact. The main point here is that the audio latent space is much more compact. It's like 40 hertz instead of like the 48,000 hertz. That's two-dimensional, so it's a bit more than just like this 2 or 3 orders of magnitude less, but it's way more compact. And there's many examples here. There's like the VAE is probably the most standard model that you can use to do this kind of latent space representations. So you can all of this you can train from scratch. You don't need any sort of labels. This is like all of this giant pre-training, and then once the decoder, the encoder, and the decoder have been trained, you don't need to do anything else. Or with the decoder, you freeze them, and then you just can focus on the diffusion model. So you have the VAEs, you have RVQs, or you have DAC. DAC is a really cool model that is actually based on RVQ, residual vector quantization, so that you can just go and take it from GitHub, and it's already pre-trained, and you can just use it in your projects if you want to. So then you can forget about the encoder and decoder, you just put them there and you just freeze them. Okay, so I'm just gonna give some examples of like, imagine that this has already been trained. So you can just put something in the text prompt like waves crashing on a hill in the ocean. You just set a bunch of randomized weights on the latents. This is like just a completely random latent, and this is what it would produce in one of the examples. So right, since the latent is completely random, if I would generate something again with a different seed of random, it would generate a different type of sound representing waves crashing on a hill on the ocean. Another example, lion roaring. And here's just a fun one, zombie eating brains. All right. So how do we actually train these models? And this is slightly different than when doing inference. What we have for these conditioned on text models is pairs of audio and descriptions of the audio. And once you have that, you basically just feed the text embeddings into your diffusion process. And then you pass the audio through the encoder that, as I said, it could be a VAE, it could be DAC, for example. And then you have the latent. And then what you do is to feed the noise, this latent noise, white noise, into a diffusion process. And what this will do is to get the latent from the audio and will distort it a little bit. And you have to specify how many steps in the diffusion process you're going to actually add the noise. And once you do that, you feed it into your diffusion big model that will try to actually denoise this process to generate the latent that will be completely clean, hopefully, of noise. And then you just decode it and pass it through and then you can listen to it if you want to. So basically, you freeze the encoder and decoder. You only train the diffusion process, and the loss. You can do many different things here, but usually you're trying to predict the error, the noise that's added, and the noise that you will basically have once you're done with all that. So you can actually predict also the latency. You can predict the direction of the diffusion process, but you can just think about it like that. So during training, you just denoise once, so that you can create a really nice batch that you will just, for each example in the batch, you will denoise from one specific point in the denoising process. Whereas during inference, you do all the denoising steps, right? That's a very nice trick that you can just do to basically speed up your training by batches. And that's the very high level overview of diffusion processes. Diffusion modeling, there's like so much in the literature. It's crazy to think that this just started this revolution like maybe 5 years ago, but it's really like the past 3 years that this kind of blew up. Okay, so now that we are hopefully all on the same page in terms of diffusion models, I'm going to talk about the first project that I want to introduce, and this is SILA. So SILA is signal-to-language augmentation for enhanced control in text-to-audio generation. This was led by our intern Sonal Kumar, and we submitted this to Signal Processing Letters. So what this is a text-based, basically, the motivation for it is that text-based models have limited control, and it's hard to obtain desired results with a single text prompt. So can we add control with minimal impact in architecture or performance? And the answer is yes, and that's basically what we're trying to do, like enhance control in text-to-audio generation. So back into our framework to train the diffusion models, what we're going to do is to actually do a little trick during training, and it's basically during augmentation. So you have the pair of audio and text prompts. And now what you do is to do some sort of an analysis or an enhancement using just digital signal processing. So you analyze the audio signal and you see what you have in the text prompt, so that you will have a different set of pairs of audio and text. And this DSP, digital signal processing enhancement, can operate on the loudness, pitch, reverb, noise, brightness, fade in, fade out, duration. We have a bunch of different attributes, and I'm going to talk about each one of them or some of them shortly. But all of these are very efficient, and they don't need like big models or anything. You can do this during augmentation, and it's very fast, and you only need the audio signal to extract some of these features. Once you have these enhanced versions of the text and the audio, you just keep going with your training as usual. And that's what we do. It's very simple. Now, some of these examples of signal to language is like, imagine that you have this audio signal that looks like this. And then you want to analyze that, right? So in the language prompt, in the text side, you have the original prompt of a thunder echoes through the sky, and that comes from your training data. So you analyze the signal and you see that the volume in terms of LKFS has -10. That's pretty loud. So you just concatenate to the text prompt, you just add a little string saying, and loudness, very loud. You analyze the brightness. You can use spectral centroid. That's what we use. Spectral centroid of 65 is relatively bright. So you say, oh, and brightness is bright. And reverb, in that case, for that training iteration, you say, oh, I'm going to add a lot of reverb. So I'm going to say the reverb is very wet. And then in the signal processing, you add some reverb there. And you just keep going for all the DSP attributes, all the attributes that you want your model to have a better understanding of. So at the end, the SILA prompt can be something like a thunder echoes through the sky, and loudness, very loud, and brightness is bright, and reverb, very wet. And the final signal output would sound like this. In this case, you would just add the reverb. So all of this is just all hand-tuned, and all of these strings are basically a set of hand-tuned rules that we come up with based on the distribution of all of our training data. And we see like, oh, we analyze all the DSP attributes of all of them, and we just cluster them manually. So it's code-wise, this is extremely simple, but yet this is extremely effective. We'll see that we did perceptual evaluations on 22 subjects, and we analyzed the state-of-the-art models in terms of each one of these attributes. And we see that most of the models, or all the models before we publish this in the literature, don't really capture any of these loudness, pitch, reverb, noise, etc., all of these attributes, because they have not been trained with that per se. We specifically, add all of this information to the model when training, so we can see that then the model is capable of understanding what's going on here. So here's some examples. Once this is trained with SILA, you would be able to do the like deep rumble of the storm echoes through the sky and loudness soft. And the sound would sound like this. So what I really like about this is that the model, for loudness, you can argue that, oh, it's just a knob. You just add the gain knob, but that's not really true. What the model is actually doing is semantically understanding that a soft thunder is probably going to be pretty distant, and you're not going to have that many high frequency components when you have the sound being generated, right? And if you have the same but loudness very loud, you'll hear like the more high frequency components. You're much closer to the thunder. Then you have a dog barking nearby with a reverb dry. Dog barking nearby and reverb wet. Here's like footsteps on a wooden floor, reverb dry. And footsteps on a wooden floor and reverb very wet. So in this case, the sound is not very wet, so it's not always working 100%. But in this way, it's a very easy way to just guide the model to add a little bit of more control in terms of what you're trying to generate. So to summarize, SILA, you added control across several different acoustic features. It's highly efficient. There's no added computation during inference, right? The only thing we do is like a little hack during training, which is basically during the augmentation process, and that's it. And it's model agnostic. So as long as your model is conditioned on text and it generates audio, it doesn't even have to be a diffusion model, right? It could be a GAN, it could be something else.
Question.
Okay. Yes.
Did you do some analysis on this as to whether this can generalize to other ways of expressing these things, or do you have to express it in the exact terms as you say, and loudness, very what it was? Can you express it in other terms or other words?
Yeah, that's a very good question. For now, we enforce that little format in terms of the text, just thinking that it would be very easy for us to, instead of let the user add that as text, have a little UI where you can just select very loud or very soft or something like that, right? So all of this would be under the hood. But if your text encoder is good enough, right? At the end of the day, you pass that text string into your text encoder, and you can use BERT, you can use T5, something like that. And if your text encoder is good enough, the result is very similar. We didn't do like a formal analysis, but we tried to using like, yeah, I want a very loud thunder, blah, 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 and it still picks it up most of the times. We didn't do a formal analysis. My guess is that it's going to be slightly worse than if you do it in this concise manner at the end. But that's a good point. Yeah, maybe in the future we could do like add them in a bit more natural way, and maybe we could prompt an LLM to say, hey, now I have this, just convert it to a more naturally sound text. Well, yeah, thanks for your question. And yeah, of course, if anybody has any questions as I go, please let me know. Okay, so this is SILA, and now let's go to sketch to sound. So sketch to sound is controllable audio generation via time-varying signals and sonic imitations. The motivation is that text prompts can be quite limiting, right? Even with SILA, right? Like even just adding all of these little additions in the text prompts with SILA. There's a lack of fine-grained control and expression, and the idea is like, can we actually control the generation via audio, right? Like when you describe a sound, it's very common to describe it with your voice. So there's a car, so you usually do or something like that. I don't know, like when we typically think of sound design, that's kind of very expressive and kind of keeping the human in the loop. And via audio, that's basically the time-varying signal and sonic imitation. That's what we mean by it. So we go back into our training framework for diffusion models. And what we do is also focus just on the training part. The latent and decoder is going to be the same. So I just rearrange the things a little bit to give some space. And what we do here is from the audio, we actually analyze the audio again. That's very similar to SILA. But instead of getting clip level features aggregated through all the clip, what we do is to get frame level features. So in this case, we have these time varying signals for several features. In our case, we have loudness, we have centroid, and we have pitch probabilities. So we analyze this. All of this is right before anything is fed into the model. We pass that through a median filter so that these time varying signals are a bit smoothed out to avoid little outliers. And then we pass this through a linear projection. Yeah, you can think of just an MLP that you put on top of these features. And then the trick here is, instead of just feeding the noise into the diffusion, what we do is to sum these linear projections into the noise of the latent. And then we just feed the latent. So now the latent, you can think of it as being a bit more structured, right? With hopefully something that we're going to train, these linear projections representing loudness, centroid, and pitch probabilities. And then you train as usual. The only difference is that you train the linear projections too, right? You need the model to understand what's going on there, and you just train this jointly with the diffusion model. And the cool thing is that this is only required during fine-tuning, and you can do this just for 40,000 iterations. And if you have like a diffusion model that's been pre-trained without any of this control, and then you fine-tune with this, you suddenly have a model that you can control with your voice or with some signal, time varying signal, right? And that's pretty much it. Here is a little video of Hugo. Hugo, I forgot to mention, Hugo Flores is the lead researcher who was interning with us last summer, who put together this, and we're actually going to present this work in ICASP in a couple of weeks in India.
Gong.
All right, this video actually went viral on Instagram. It got like over 5 or 6 million views. I don't know, kind of crazy. And just to illustrate that this works with signals beyond vocals. Here's Hugo playing guitar and using the output of the guitar as the input to the sketch to sound model. All right, so to summarize, sketch to sound, we add control generation with audio. So we have really fine-grained control for your sound generations. And we keep human in the loop. That's really cool because you, with your just a simple mic, you can create really cool sounds for your creations. It's very efficient method and it's model agnostic. Like as long as you have a diffusion model that is conditioned on text, or it doesn't even have to be conditioned on text, honestly, but it's actually more powerful. So if you have that, you can just add that little MLP and this little technique during training, and then you will have this just fine-tuned for 40,000 iterations, and you get it. So this is sketch to sound, and I'm gonna move to
Question.
yeah.
Have you considered using the video as input to the generation process?
Oh, that's the next model. That's the next model I'm going to
Okay.
talk about.
Okay.
It's a great segue question. Thank you. Any other questions? Okay, I'm gonna keep going. And now let's talk about MultiFoley, which is actually video guided Foley sound generation with multimodal controls. This was led by our intern Zheyang Chen, and this is a work that's gonna be presented at CVPR this year. I think that's in June. And yeah, perfect synchronization with video can be tedious if you have to try to, even with a sketch to sound, right? You try to be on time all the time when you're doing your vocal imitations, if you're doing it with vocal. So can we use videos as an additional condition for the generation, as Olaf was already asking himself? And how about a combination of text, audio, and video conditions so that you have this multimodal, you have this multi-Foley approach to Foley? So the answer is yes, and that's what we aim to do with this project. So the idea is actually quite simple. We go back into our training diffusion framework, and I'm going to, again, rearrange things a little bit. So in this case, instead of just having pairs of text and audio signals, we have triplets of text, audio, and videos. And what we do with this is basically take an off-the-shelf video encoder. Sorry. We actually use the one from DFoley, which is this one called CAVP features that basically understands video and returns video latent for these encoders. And what we do with these video latents is that they are in a different sampling rate than the latents that come from audio. So what we need to do is to add a resampler so that the latents of the audio and the latents of the video are on the same framing rate, the sampling rate, if you want. Once you have that, we simply concatenate the latence of the video and the resampled the resampled latence of the video and the audio latence. And we concatenate them across the channel dimension of your tensor. Once you have that, that's basically it. The idea is that you concatenate across the channel's dimensions, as I said. And the other trick actually is that the video latents are masked during diffusion, so that we are not trying to generate the video, right? We're only trying to generate the audio, but the tensor and the information that the model is going to see is the video and the latence, so that once you do inference, you still add the video latence there, even though you're not generating them. And that's basically it. So let's see some. Oh, what's that? Okay, there you go. So let's see some results. So this is a video that has no audio, and then we feed the video to our model, and we condition it via text of what we actually want. And in this case, we say bird chirping. So you can see that it's pretty synchronized to the movement of the mouth of the little bird. But we can then become more creative and do more fun stuff. So instead of bird chirping, you could say like rooster crowing. Or male speaking. Oops. Okay, or sheep bleating. Okay, I have a lot of examples here. Here's the typewriter. Again, the video is completely silent. We just created this video with the output of our model in terms of audio. So we mix them together. And here we have typewriter. I'm not sure if Zoom is actually messing up with the frame rate of the video or the audio synchronization, but it's really synchronized. You should check out the website. It's really cool. So instead of typewriter, you can say a piano. Or a keyboard from like a computer keyboard. All right. Okay, some of the latest examples. This is cello. I really like this one. I really like that the video, the model understands from the video the vibrato. And it also understands kind of that if you go down your neck in your cello, it's going to be higher pitch. So it's really cool that it understands that. So cello, but what if you just put an edu? Or a chainsaw. Even the chainsaw has some sort of a weird pitch. Okay, cat meowing, lion roaring, horse neighing. Okay, so to summarize, MultiFoley, basically it's a method to generate audio from video. And here you can have multimodal control. You can use video, you can use audio, or you can use text. And you can go to the website of this project and you'll have like different modalities. So the examples I showed basically use all of them, but you don't need to. And one thing I didn't mention is that, and a big part of the paper is that the high quality output that you can get even when trained on low quality video data sets. Like in our case, this was trained on VGG sound. For those who are familiar, this is a data set that is very low quality in terms of the audio quality that you have, but you have video and audio. What we did is we have an internal audio only data set that is very high quality. So once we combine them and using some classifier-free guidance, we are able to produce high quality audio sampled at 48K. Okay, and that's pretty much it. To close out, I presented SILA, which is enhanced text control for sound generation. And I presented Sketch to Sound, which is voice control or audio control for sound generation. And MultiFoley, which is video control. And I wanted to let Foley artists talk about the future that is coming instead of me, myself, talking.
Joanna's mastery of her craft is unique, and even in the digital age, she feels the role of a Foley artist is still vital to storytelling.
I can imagine a future where machine learning aids us in Foley, but I do not ever believe that it will take away the simple and beautiful performative nature of it.
And I fully agree with her. And with that, yeah, these are some references. I'll share the slides, and that's it. Here you have the QR codes for the archive papers for each one of these publications. And that's all for me. Thank you so much.
Thank you, Oriol.
I had a question, Oriol.
Yeah.
So about the MultiFoley, I maybe I understood it incorrectly, but in the diagram you showed, you explained that you could input text, video, and audio. Is that right?
Mm-hmm. Yeah, that's
But
correct.
is that for was that for the training, or is that would I be able to input an audio file that has nothing to do with the video and then a text prompt? That's because the examples you showed, you only inputted video and text and outputted audio for the video. But did you guys try to mix audios and videos that weren't related?
Yeah. And in the demo, in the web demo, we have examples of, for example, we have this type of sound that we like, and then we just add that audio instead of text or with text to basically generate sound synchronized with the video input, if that makes sense.
Mm-hmm.
So yeah, you don't need text, and in fact, you can just feed one of them and it's gonna work, which is the magic of these models. But yeah, that's something that the model is capable of. Mm-hmm. And yeah, I suggest going to the website and checking out the demos, because there's a lot of them. I just showed like some of them, but there's a lot of different modalities and what you actually can do with the model.
Will do. Thanks.
Yeah, of course. Any other questions?
Yeah, thank you for your talk. I have some questions. I guess I'll start with the one that I find. Yeah. Anyways, I'll start with this one. So you guys are doing a lot of audio generation. Are you also working on some sort of audio watermarking for generated stuff? So since there's a lot of regulation up that is coming that is gonna demand some sort of like generated content to be detectable, is this something that your group is also looking into or considering, some sort of watermarking as part of your models?
Yeah, that's a great question, and I want to start with saying that anything that we put into a product has only been trained on data that we have license on. Adobe is really, really strict on this. And yes, here, like MultiFoley is trained on VGG sound, but we don't have this in any Adobe product. Okay, I just want to say that real clear, because we couldn't. We don't have the license of this, right? So that's to start with. And then the second thing is like, we are some groups at Adobe Research do have fingerprinting for this. The problem with sound design is that it can be a very challenging problem in terms of like in our data sets, for example, we have, I don't know, we may have dozens of thousands of door creaks, for example, door creaking, door opening, or just door shutting down. So it's really hard to say, oh, did the model regurgitate something from your data set, or did it just create it, when it's something that it's even for a human might be very hard to tell. And despite all of that, we do intend to avoid these situations, and we have ways of analyzing the potential regurgitation of the model. So we want to avoid that. So we compare the output. Once the model is trained, we compare the output of the model when using one of the prompts that it was trained on, and then see the difference between the output of the model and the actual original waveform associated with the text that was trained on. And we haven't seen any of these regurgitations. So the models are not, like, we have so much data that the models don't seem to regurgitate or like to reproduce any of the training data. But again, for sound design, it's not as an easy problem. I'm not saying it's easy, but I think for something like music, this is way more crucial than oh, you're using that door closing instead of that other door closing. It's a bit harder to tell.
Yeah, sure. I was kind of like more thinking, so if I use, for example, some of the products that you guys are working on, and I use some of the audio that has been generated, if I put that out there, is there a way for anybody to know that that audio was generated from an AI? That's my point. So
I see.
Yeah. So is that something that you're thinking of? Because that's coming up, at least in Europe.
Yeah. Sorry, I completely misunderstood your point. The watermarking of the we are not watermarking, right?
Exactly.
That's the answer.
Yes. So that's my question. Is like if that's something that you guys were considering, but yeah.
Yeah, so that is related, right, with the fingerprinting, to understand whether something comes from some training data or not. But right now, as far as I know, well, we're certainly not doing that, and maybe there's other groups of audio at Adobe that may be doing that, but I'm not sure. I believe that the music group has been exploring this, but yeah, it's something that we may need to do it. For now, we're like, hey, we're like, you can generate these, and I'm not even sure what is the license for that. Like for the right now, what we have in the product in Premiere Pro is the generated extension of the video, what I showed before, that you can also extend the audio. But I'm not even sure what's the once you extend your own audio, what is the license for that. Yeah.
And I just have a quick other question that I guess is easier. If you're controlling your diffusion model with audio, how good do you have to be at doing the sound? Because you are pretty good. I think Justin is also pretty good at doing the roar. I think I wouldn't be that good at doing that roar. So, like, especially I was thinking for sounds that maybe vary a lot, like something that goes on by tick, 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 or something like this. Like, how precise do you need to be?
Yeah, that's also a very good question. The thing is that as long as you are on time, like you are good at synchronizing with the video, then you type the what you want it to convert to, right? So in that case, yeah, like, I don't know, maybe if you start whistling and use that as a prompt for something that doesn't have anything to do with whistling, like, I don't know, like something sudden, like a door closing, it might not work. It like it's completely out of distribution of what the model has seen during training. But if if you are trying to produce growls, and instead of doing like something like or something like this, you do like like it would still work because it gets the loudness. The pitches might be a little bit off, but it will know that, oh, okay, this is the loudness, this is the RMS curve basically, and I'm just gonna follow it, and I know that at least it's not like something sudden. It's something that's kind of the RMS of what a real growl would sound. So the model is capable of doing it.
Yeah.
If it's completely out of the distribution, it fails. I mean, it does something that I think it can be quite creative if you just let it out there in the world and people let just play with it. That's one of the things that excite me the most. Like, hey, I want to put together a technology for the creators to break it and create amazing things with it, right? Like nobody thought that, with the electric guitar, someone would play it. I don't know, like the way Jimi Hendrix was playing. It's like, what? This is not meant to do that, but there you go. That's what art and the human expression comes from.
I think I have a related question. In the MultiFoley example here, it seems like the generation takes the cues from the videos onto for the time sync, more or less, and the kind of the sound that it generates, it takes mostly from the text prompt. Is that something that you did on purpose, or is it something that just happened to turn out this way?
Yeah, so it's a good question. And it's related with this out of distribution and what happens with it. And one of the caveats of this model is that if you don't have text prompt, if you just like have full video to audio generation, the results are not that good, or the audio is not that high quality. And the problem that we have here, it's because we didn't have access to a very good high quality video and audio synchronized data set. So we had to leverage this low quality VGG sound data set. And because of that, what we did was to do a little hack. We basically just did classifier free guidance to during the diffusion process to guide the model, the denoising process, away from the distribution of the sound of VGG sound and guided more towards the distribution of sound of the high quality just audio data that we had. And to do that, we used text. The classifier pre-guidance, what we did was we just concatenated text at the end of each text from the low quality data set by saying description, blah, blah, and at the end we say low quality. And for the other, we did text high quality. And then that, with the classifier free guidance, we were able to guide this. So that's why we believe that the model is actually relying a bit too much on the text. And that's why if you don't have text, the results are not that good. But again, this kind of adds the functionality of now you can do things that kind of are out of distribution in terms of what it's seeing and associated text with the video, and it still produces something that is meaningful, as we saw, like I don't know, a cat producing a lion roar.
Thank you.
I had a question.
Yeah.
Yeah. Hello, Ori. Thank you very much for the talk. Very informative. I learned that there are different ways of, the models which you spoke about, like only text, audio text, and the video text models. Have you also explored, say, a model which takes double audio plus text input, say, audio which are in the extreme ends of a spectrum, say, I want to generate a violin audio which is both very intense and also calming, belonging to the same scale, or a dog barking very angrily and then very playfully. Will the model be able to generate an audio and then, mix sort of from both of these samples?
Sorry, I'm not sure if I understood correctly. It's like you mean like starting from like a dog like very quiet to a dog very loud and angry and vary throughout the generation. Is that?
Yeah, yeah, very in between, like very angry and then very playful, angry, in different intensities.
Yeah, so that's a real point. The model is not capable of doing something like that right now.
Yeah.
If you want to generate a sound, you have to specify what type of sound you want. What you
Uh,
can do actually, and I think we have examples of that, is if you have a very angry dog sound and imagine you have like a video and you take half of this video, very angry sound, and you feed it to the model, and then you in the text prompt you say, hey, I want to generate like a very quiet, friendly dog. Then the rest of the generation, it will generate the quiet dog, and it will continue the audio because you can just mask the latents. And
okay.
that kind of audio continuation, you could kind of guide it so that it creates this kind of blend
Right,
style.
right.
But
Hmm.
yeah, in terms of like you tell the model, I want to generate a very loud dog and then a very quiet one, and generate it. I would think that the model would fail at that.
Yeah, the only reason I asked that is, say, in some musical pieces, say in Western pieces, it goes on and then it goes to a climax, and then it's sort of not so intense. So I thought it would be useful in those cases, say in violin or Western pieces. That's it. Yeah,
Yeah, no, it's like a really great point.
thank you.
I have another question if nobody wants to go for it. I was just wondering about the length of the time in your generation. So I guess this cannot go on forever, right? At some point it crashes. So like how like what is the maximum that is still relatively good?
I believe these models are trained on 10 seconds
Mm,
audios,
mm,
but it really depends on your GPU memory. Uh, like like if we were able to feed I don't know, like 1 minute of latents into the GPUs and have that trained in batches, um, that that would be possible. We've actually tried with 30 seconds into beefier GPUs, and it was pretty good, but it's not as good as like we've tried with 30 seconds on models trained on 8 seconds. And uh, yeah, the model is better if you try to with 8 seconds, but it works if you just extend it because once the model is trained, you can just put it for inference in a
mhm.
bigger GPU. Um, but yeah, I guess it's a matter of the GPU. And then what I would say is that if you can and if you really care about these longer type of generations, then you will probably want to train the models on also bigger GPUs with your ideal specified length in time in mind, so that you set it to. Yeah, but yeah, it's kind of crazy how flexible these models are. Like yeah, like even if you change the latent size, then it kind of understands like, okay, I'm just gonna continue producing the sounds that you want. If you want to have longer, even longer, like 10 minutes or something like that, we've never really played with this. I know that the music group in Adobe Research, they are able to generate like very long generations. I don't know what tricks they use though.
Cool, thank you.
I think there's a bunch of, especially in the music, and not for sound design, because usually for sound design you just need like short sound effects. But in the music generation domain, there's a lot of efforts to try to generate like 5 minute song or something like that.
I wonder if the model could learn or could output a sound length that makes sense, like maybe like a gong, like the example that you showed from Justin going like bong, maybe that has more like kind of like tail of, than something short like a clap, So I'm wondering if the model could also somehow learn that. Anyways, this is just like tangent.
Yeah, no, that's a good point. I didn't mention at all how long these models are.
Questions.
Hey, Bexy.
Yeah, go for it.
Why are you not doing music generation?
Yeah, that's a good question. I don't know. I feel like I had the opportunity to be working on this more of a different domain for me. I've been working with music for so long, and I thought that there was an opportunity for me to expand a little bit towards other audio domains. And I still collaborate with the music group a lot, and we published this mirror last year. And yeah, I think that's the answer for now. Like I just had the opportunity to be working on this, and I've also been it's been quite fascinating. Like now I watch movies and see series, and it's like, oh yeah, it's fascinating, the sound design. Like I've been watching White Lotus, and I've been watching it on like 5.1. It's incredible, and it's so creative, and I keep thinking about, oh, how can I contribute to this in a way that is meaningful, and in a way that is like very human centered, so that it's just unleash the creativity, instead of having a robot. You just type the text and that's it, right? Like I think that I've been working with music for so long that this is kind of exciting to me to go to a slightly different domain, that it's still audio. But yeah, I mean, I may be working with music again. It's my passion, and I play music all the time. So it's always there, part of my life. Highly recommended to watch White Lotus and this 5.1. It's absolutely incredible. It's crazy.
Speaking of 5.1, do the models consider several channels, or do you output mono sound and then post-process it?
Yeah, so I think in the publications, I think all of these are mono, but maybe one of them is stereo. But we now been operating in stereo. Some of the latest research that we've been doing, and the only thing you need to do is you have to have a bigger, beefier autoencoder. Like you can just train your RVQ or the VAE with more channels, and then you can do some tricks there, but that allows you for stereo. We haven't gone beyond stereo, but that's something that we're interested in pursuing, to go to the ambisonics space, because I think that's super interesting. And in fact, Hugo Flores, the main researcher behind the Sketch to Sound, has been playing with Sketch to Sound in a crazy art installation of, I think, like, I don't know, like 16 or something speakers, and he has like this little interface where he can just point where he wants the audio to come from. But yeah, that's something that's definitely under our radar, and we want to expand. For now, it's just stereo.
Cool. So
all right,
that's gonna wrap up this seminar. Thank you very much for this exciting talk. Welcome back next week, March 27th. We'll have Maria J. Molina talking about machine learning for Earth system prediction and predictability. So welcome back.
Thank you so much. Thanks for having me. It's been a great pleasure. And yeah, hope to see you soon. Thank you all.
Thank you, Udi. Bye.
Take care. Bye-bye. Thanks.